Video, we're going to learn about the concept of eigenvalues and eigenvectors for a matrix. So I start with the definition. Given a square matrix A, and by the way, you can only have these for a square matrix, an eigenvector is a non-zero vector x with associated eigenvalue lambda if they satisfy the equation ax equals lambda times x. Now at first this seems to be coming out of nowhere. Here's this random equation we want to satisfy. And so let me give you a little bit of justification for why we care about something like this. So the idea is we've learned how matrices represent linear transformations, and some linear transformations will rotate vectors, some will stretch them, some will shear, all sorts of different geometric interpretations here. But what this is saying is that for this matrix A, it has a special effect on a certain vector x, that if you start with the vector x, that the output is going to be lambda times x, and when you multiply a vector times a scalar, it's going to be parallel to it. So it's either in the same direction or opposite here. And so this lambda just tells you how much you scale it. But the thing is that this vector is in some sense a special direction for A, the matrix A, because when you multiply it, you get out the same direction, just possibly a different length. So just a random little idea that may help you understand this. If you think about if you're doing some sort of system, maybe pushing someone on a swing, and if you push them at just random times, you're most likely going to mess up their swinging motion, and it's not really going to help them. But if you push them at just the right time, you're going to be able to reinforce it and keep it going in the same direction, back and forth, and increase the magnitude of it. So the idea is this is like the right direction here, that when you apply the matrix in this particular direction, you get output in the same direction. It's reinforcing it in some sense. Now again, we're not really dealing with that here, that physical interpretation, but I'm just trying to give you an idea for how eigenvalues and eigenvectors work. Again, the eigenvector is the direction, the x vector here, and the eigenvalue is whatever you multiply the lambda times the original eigenvector. Now, how are we going to find them? Well, we have a nice little theorem that tells us this, that if I want to find the eigenvalue, I will solve the equation determinant of a minus lambda I is equal to 0. And I tell you right here in the theorem this is going to be a polynomial equation, so we're just going to solve it. We can factor it, maybe use some other techniques to solve, quadratic formula, etc. Whatever helps us solve the equation. And then once we've found our eigenvalues, lambda, whichever ones we find, for each one of them, we're going to be able to figure out the eigenvectors by looking at the null space of the matrix A minus lambda I. And the reason why is if you have, AX equals lambda x, well, you can think of lambda times x as lambda times identity x, because multiplying by the identity doesn't change the result, right? That was something we had before. And so if that's the case, then we can move things over. AX minus lambda IX equals the 0 vector. And then we can go ahead and factor out the x there and get A minus lambda I times x equal to 0. And so again, we're looking for solutions of this equation, which is exactly going to be the null space of the matrix A minus lambda I. And we've seen how to find null spaces in previous videos. So okay, now let's go ahead and do one example of this. We're only going to do a 2x2 matrix example because they're relatively short and quick and easy to work through. This same process would work for 3x3s or 4x4s or whatever size matrix you want to look at. It's just the same thing but longer and more tedious. So we go ahead and we start with our matrix A. In this case, it's 1, 2, 2, 1. And we always have to find the eigenvalues first. So that means we write down the equation determinant of a minus lambda I equal to 0, well, that's going to be the determinant. The matrix A is 1, 2, 2, 1. Lambda times the identity matrix. And then if you think about this, it's going to be 1, 2, 2, 1 determinant minus lambda 0, 0, lambda. And this is the determinant of going to be 1 minus lambda 2, 2, 1 minus lambda. And we know how to take our determinants here. 1 minus lambda times 1 minus lambda minus 2 times 2. We can go ahead and simplify some things here. It's going to work out to be lambda squared minus 2 lambda minus 3. And we set that equal to 0. We're trying to solve this equation here. Generally, we're going to be given examples where we can factor it. And we can factor this one. Lambda minus 3 times lambda plus 1. And so we're going to get two different eigenvalues here. Lambda is 3 and lambda is negative 1. So here are our eigenvalues. That's only the first step of the problem, though. We also need eigenvectors. And again, an eigenvector is going to depend on what eigenvalue you have. So there's going to be an eigenvector for lambda is 3, and there's going to be generally a different eigenvector for lambda is negative 1. And we need to find each of them separately here. So to do that, we will start with lambda equals 3. And we're trying to find the null space of a minus lambda I. So we're going to go ahead and do the a minus lambda I. Remember, lambda is 3 here. So 1 minus 3 is negative 2, 2, 2, negative 2. And since we're trying to find the null space, our process was we go ahead and put it equal to 0 there. Then we're going to do our row operations on this. Really not much work to be done there. It's going to be 1, negative 1, 0, and then a row of zeros here. And then now that we have our matrix in reduced row echelon form, we see that we have one pivot, we have one free variable. We're going to go ahead and call them x and y for simplicity's sake. So then my equation here would read x minus y equals 0. So that means x equal to y. So then we would have, okay, the vector xy is equal to yy, because x equal to y. So that's y times 1, 1. And that vector 1, 1 is going to be our eigenvector. So the first thing we get is lambda is 3 with an eigenvector of 1, 1. Now we're going to repeat this for lambda is negative 1. And if we go ahead and do that, we're going to get 2, 2, 0, 2, 2, 0, just by working out from the original matrix A and subtracting the lambda times the identity. You can do your row operations there. It's very similar to the first one with positives, though. We get the equation x plus y is 0, so x equals negative y. So xy is negative y is y times negative 1 and 1. And that means our other pair of eigenvalue eigenvector is lambda is negative 1 and the eigenvector is negative 1, 1. I do want to point out something really quickly here, is that there is not just a single eigenvector. In fact, there's always going to be infinitely many different eigenvectors. You just plug in different values for your free variable. So for example, if you plugged in y is equal to 7 or something, then you'd have the vector negative 7, 7, and that would be a different eigenvector, and that's fine. Generally, when they ask you a problem here, they just want you to find any single eigenvector. It doesn't really matter which one you find. But this is our process here for how we do this.